All right, Calculus Rock Stars, welcome to Unit 3, Day 6 notes. Miss Bowman is at the end of her wits filming these today, but I am here. We're going to go through the Day 6 notes and kind of wrap up and finish up this algebraic unit on the rules of differentiation. And so we've learned in theory all the derivative rules. So any type of function that we have learned in math 4, minus the polars, we have now learned how to find the derivative of that function, including parametric. So we've kind of dealt with every function there was in our math 4 year. Now, what today and next lesson's focus is going to be is what happens when we don't have a function. Okay, what happens when we have, I don't know, a relation? Okay, how do we find the slope at the points on a graph that is just a relation, that is not a function? Most of relations are going to be what we call implicitly defined. Okay, so we're going to talk about the difference between implicitly defined equations and explicitly defined equations and how we find the derivative of each one. And then talking about specifically implicit equations today, how do we find a derivative rule or derivative expression for implicit equations? And then how do we use that to solve problems? So that's kind of our goal today. And we're just going to get on it. So what is the difference between an explicitly defined function and an implicitly defined function? Okay, explicitly defined functions are saying if you plug in a given independent variable, then I have a rule to get the output or the dependent variable. So a lot of times what that means is that our equations are going to be y equals. It's giving me what the output is for any given input. For example, this is an explicitly defined equation. It's all the equations we've been doing so far. An implicitly defined equation just kind of relates the two variables together, not really assigning who's independent and who's outdependent, or who's outdependent, independent versus dependent. Okay, but it kind of relates them together. Now, if we look at these two equations, are these two equations the same graph? Yes, but the way they're defined, this one is defined for y, whereas this one is just a relationship between x and y. Okay, now this graph has a slope. The question then is, how do we find the slope function? Explicit functions, okay, if I wanted to find the derivative here, or y prime, I could call it y prime too. If this is a linear function, we know its derivative function is -2. If it's implicitly defined, it can be a little harder to tell, but we can kind of use what we do here and apply it to this situation by just kind of taking the derivative of each piece with respect to x. Okay, so for this one, if I wanted to take the derivative of 2x, it would just be 2. If I wanted to take the derivative of y, now here's where the problem comes. Y in this case is the actual dependent variable. It's the output variable. It's the function, okay? Its derivative would not be 1 because we're not taking the derivative with respect to y. We're taking the derivative with respect to x. So this little dx at the bottom tells me that x is the input variable, which means y is an output variable. It's a dependent variable. It is a function. So its derivative is a function. Now we call that function dy dx or y prime. So here I could say, okay, if I have a y, its derivative would just be a function I call dy dx. And then the derivative of 5 would be 0. Now, this is a relationship that gives me the slope. It's just not explicitly defined for the slope. So if I get dy dx by itself, I get dy dx equals -2, which is the same thing I got when it was explicitly defined. It's the same idea as f of x, okay? F of x is a function. Its derivative is another function we call f prime. So let's look at a little bit more complicated. Let's say I have a relationship here. This is like for my future engineers and like people who are going to save the world, okay? These are the types of situations we have. We have constraints and relationships that have a lot of different variables that go into the world. The world is not just two-dimensional. It doesn't always have just an X and Y. A lot of times there's multiple different effects or multiple different variables that play. And so we kind of have to think about like more complicated expressions. Now, if I wanted to find the derivative with respect to X in this equation, that means one of two things. Everything that's not an X is either a function of X or everything that's not an X is a constant. For this example, we're going to treat everything that's not an X as a function of X. So everything not equal to X is a function of X. Okay, so let's see what that means when I take the derivative. So if I take the derivative, what we say implicitly, I'm just going to take the derivative of this entire equation. So when I do that, the derivative of y is a function, so its derivative would be dy dx. The derivative of x cubed, well, that's just an x. That's our variable. That's just going to be 3x squared. Now, this is where we get interesting because z is considered a function of x. So this is like saying f of x squared. If you look at this, guys, this is chain rule. There's a function z that's being squared. There's a function inside of a function. So I'm going to use chain rule here, and I'm going to bring the 2 down. Now it's going to be z to the first times the derivative of z, and if z is a function, its derivative would be dz dx. Okay, plus, all right, now let's do this. Ooh, another chain rule. So the derivative of cosine is negative sine, so I'm going to say minus sine of 5h times the derivative of 5h. Now again, we're going to treat h like a function of x. So that's the same thing as saying 5f of x's. So if I take the derivative of 5f of x's, it would be 5f prime of x's. So this is just going to be 5 dh dx's. And I'm using the slope notation here mainly because I want to honor who is the actual independent variable. Okay, plus the derivative of z. Now again, z is a function. Its derivative would be a function in terms of x. And then plus the derivative of 3 is 0. And that would be an equation that relates those derivatives or those rates together. Now we could kind of do the same thing, okay? What if we want to take the derivative with respect to z? That means everything not equal to z is a function of z. Well, how is that going to change things? Well, the first part isn't going to change. So if I have y, and y is a function of z, its derivative would be dy dz, if I use Lenny notation. Now here, x is no longer the independent variable. It's now a function. So I'm going to use chain rule here because it's being a function being cubed. It's similar to this idea right here. So it'd be 3x squared times the derivative of the function, which would be dx dz if I use slope notation. Equals, okay, now z squared, if z is the independent variable, I'm just going to take the derivative of that expression like I would if it was explicit. Minus sine of 5h times 5 dh dz plus the derivative of z would be 1 plus the derivative of 3 would be 0. Okay, I could do the same thing with respect to y. I could do the same thing with respect to h. Okay, these are extreme examples, but it just gives you the idea that variables and expressions are either constants or they are functions. And if they are constants, their derivatives are 0. If they are functions, their derivatives are other functions that we usually name either with prime notation or slope notation. Okay, so implicit differentiation is a technique that we use for implicitly defined relations. I'm not going to say functions. I'm actually going to say relations because most of these things are not functions. Okay, so for example, x squared plus y squared equals 25. Now, if you remember what this graph is, it's a circle with a radius of 5, center at 0, 0. Okay, if I look at these points, do these points have slopes? Yes, they do. So there's got to be some sort of expression that I can use to find the slopes at these points. Now, there are 2 points here that don't have slopes, and I just kind of want to make a note. There's no slope at there. Those would be vertical tangents. And maybe the derivative expression will help us find that. But what we would do here for our steps is, I don't know why this keeps popping up to you. Okay, so the steps to using this process. Step 1, take the derivative with respect to x from left to right. Okay. Now, that's going to give you a relationship between x, y, and the slopes. So your second step is just to isolate the slope expression. We want an explicitly defined slope expression. And so we're going to get an expression that has a dy dx in there, and our goal is to get dy dx by itself. Usually how that's going to look is you're going to move all the dy dx terms. And I don't have to use dy dx. I can say y prime. I just use dy dx because it helps me. Because then I can tell the difference between a y and a y prime pretty easily. I have a trouble telling the difference. Whereas if I write dy dx, I'm not going to confuse them. So we're going to gather all the dy dx terms on the same side, and then we're just going to factor dy dx out. Okay, so we're going to do an example with a circle. And then we'll do a couple other examples, and then we'll be done for the day. So it's a little bit of a shorter lecture. Okay, so here we go. X squared plus y squared equals 16. Again, this is a circle with a radius of 4 this time, a center at 0, 0. All of the points on this circle would have slopes except for -4 and 4, which would be undefined because there are vertical tangents there. But let's see if we can't find the slope of the tangent line at the point 2 and 2 root 3. So this point right here, I want the slope of that line. I know it's going to be a negative slope, so that kind of helps me. So I can at least verify my answer. So I want to find the slope of the tangent line, which means I need to find an expression for dy dx. So we're going to take this implicitly defined equation, and we're going to find an expression for the derivative. Now, loves, you can solve for y and make this explicit. So if you want to get y by itself and move the x squared over and take the square root, you would actually end up with two functions. Okay, a positive square root, which would be the top half of the circle, and a negative square root, which would be the bottom half. Since we're on the top half, we would use the positive square root, and you could take the derivative of this using chain, okay, and then plug in your point. That would work. That's 100% a valid reason. It's just not the most efficient way. If we are going to do implicit differentiation, what you're going to do is you're going to take the derivative of both sides of our equation with respect to x. So I'm going to take the derivative of the left, and I'm going to take the derivative of the right. Okay, now, when I do this, I have to remember x is the independent variable. So when I take the derivative of x squared, it's just 2x. Now, when I take the derivative of y squared, guys, y is a function of x. That's the same thing as if I had f of x quantity squared. This is a function inside a function. It is a chain rule. You are going to know, love, honor, cherish, and marry the chain rule. So when I take the derivative here, I would do the outside, which would be 2, bringing the 2 down, times the derivative of the inside. So I did that in f of x notation because you're a little more comfortable with that. But here it'd be the same thing. I'm going to bring the 2 down. So it's going to be 2y to the first times the derivative of y, which if y is a function, its derivative is just dy dx. And again, you can write that as y prime. I just have a hard time differentiating between the two, so I write it in slope notation. And now here, the derivative of 16 would just be 0. Okay, so now I have an equation, a relationship that has a dy dx in it. Okay, this relationship gives me how the slope is related in this circle. So all I got to do from here is make this explicitly defined for the slope. I know that 2 times the x coordinate plus 2 times the y coordinate times the slope has got to be equal to 0. So if I get the slope expression by itself, so first I'm going to move that 2x over. Then I'm going to divide both sides by 2y. Now I have a slope expression. dy dx equals negative, I see the 2's would cancel, x over y. So here is a slope expression. It's a rule that will calculate the slope of this circle at any point I want. The biggest difference between an implicitly defined derivative and an explicitly defined derivatives are always just in terms of x. Implicitly defined derivatives can be in terms of x and y, or y and or y, okay? So what that tells me is that if I want the slope at the point 2 comma 2 root 3, I need to plug in both the x coordinate and the y coordinate to find the slope. And it gives me negative 1 over root 3, or negative root 3 over 3 if you want to rationalize it, which that seems reasonable. And that's how you would do it. Okay, so let's do a couple more practice. So here is just some expressions, and all I want you to do is pause me and differentiate the following with respect to x. So when you take the derivative of each of these pieces, if it's not an x, it's considered a function of x. So go ahead and pause me and find the derivative with respect to x for each of these terms. Okay, so let's see what you got. Derivative of x cubed. Now x is the variable here. Its derivative would be 3x squared. Now b is y cubed. Its derivative, y is not the variable, y is a function, so its derivative would be 3y squared times the derivative of y, which is dy dx. Or you could write it as 3y squared times y prime, okay? Again, I don't like this because then sometimes I think that's a 1 as opposed to a prime. I prefer the slope notation, but either is completely accurate. All right, let's go to C. X plus 3y. If I take the derivative with respect to x, the derivative of x is 1. The derivative of 3 times y, well, y is a function. So the derivative of 3 times y is 3 times dy dx. So I'm just using the constant multiple rule here, and the derivative of y is dy dx. Last one, x plus y squared is just going to be 1 plus, again, this is a function in a function chain rule, so 2y times the derivative of y, which I'm just going to call dy dx because it is a function. All right, so why don't you try this one? Find the derivative expression for this equation. Now, if you're like, oh my God, you just went from 0 to 1,000 real quick, it's okay. Try your best, pause me, and then we'll go through it. Okay, let's see here. It's definitely implicitly defined. It's got x's and y's together. It's a relationship between x and y. I know I'm finding dy dx, which tells me x is the variable and y is considered a function. So I'm going to go from left to right. So when I take the derivative starting from the left, the derivative of y cubed is 3y squared times dy dx. Again, I'm using chain rule there. Plus the square derivative of y squared would be 2y dy dx, minus the derivative of 5y would be 5 dy dx, it's constant multiple rule, minus the derivative of x squared is just 2x. Now you're like, Ms. Bowman, can I write dx dx? Yeah, absolutely, but dx dx is saying, how does x change as x changes? It's just 1, so it doesn't really matter, and then the derivative of negative 4 is 0. It's not always 0 over here, it just happens to be 0 in these cases. Okay, so now here I have a related rates equation. I have a relationship that has a dy dx in it. My goal is to make this explicitly defined for the slope. So I'm going to try to get dy dx by itself. So first I'm going to move everything that doesn't have a dy dx to the other side. So I end up with 3y squared dy dx plus 2y dy dx minus 5 dy dx equals 2x. Okay, when in doubt, factor out. If all three of these terms have a dy dx, I can factor it. And then I can divide by that quadratic, and I get dy dx equals 2x over 3y squared plus 3y minus 5. And there's my derivative expression. Implicitly defined for x and y. Since the function started implicitly, most likely the derivative would start implicitly. Now you could try to get this explicitly defined from the get-go, but I'm not trying to solve for y here when there's a y cubed and a y squared. So for me, the implicit way is easier. And then the biggest rule of thumb is anytime you take the derivative of a y, you have to tack on that times dy dx for chain rule. Okay, now let's try two more and we'll call it a day. So for this one, find the slope of the tangent line at the point 1, 2. Okay, for x squared minus xy plus y squared equals 7. This is a common implicit equation. It's some sort of like, I don't know, ellipse looking thing. Okay, but they do love one that looks like this. If it's implicitly defined, again, we're just going to start from the one from left to right. Now, one thing I am going to have you watch out for. Do you see this right here? Do you see how it's an x next to the y? Okay, that means those two things are being multiplied. That is a product rule. So beware the product rules. That's where people tend to make mistakes. So I'm going to start from the left. I'm going to take the derivative of the left side of the equation. I'm also going to take the derivative of the right side of the equation, and we'll go from there. So the derivative of x squared is 2x minus. Now I got to take the derivative here, and again, this is a product rule. This is my u, this is my v. So u dv, the derivative of y is dy dx, because it's a function, plus v, which is just y, times 1, because that's du, and that would be the little product rule, plus, now we keep going, the derivative of y squared, again, chain rule, chain rule, chain rule. It would be 2y times dy dx equals the derivative of 7, which is 0. So now I'm just going to start cleaning this up a bit. I'm going to like distribute that negative in. Y times 1 is just y. And now your goal is to take this expression and make it explicitly defined for the slope. So I want to get this by itself. I'm going to subtract 2x and add y to both sides. Okay, that leaves me with negative x dy dx plus 2y dy dx equals negative 2x plus y. From here, I can pull out the dy dx. And then I'm going to divide both sides by that fraction, and I get negative 2x plus y over negative x plus 2y. Now, unfortunately, we look at this and we're like, can we cancel anything? Can we cancel out those negatives? No. Can we cancel out these x's? No. These 2's? No. These y's? No. Addition and subtraction is like glue in the fraction. The only thing I will say is that sometimes the AP exam likes to make the front term positive. So it'll pull out a negative 1 from both terms, because then those negatives would cancel, and that would leave you as 2x minus y over x minus 2y. So if you ever end up with the exact opposite answer, you're probably right, because they just probably factored out a negative. Okay, so especially when you're doing your homework, if you end up with this answer, but the back of the book says this, just pull out a negative 1 and see if that makes it match. If they're the exact opposite, if every term is the exact opposite, then your answer is the same, which is a little weird to say. Okay, let's try one more. Let x equal sine of y, find dy dx. Okay, I'm going to go from left to right. So we're going to take the derivative with respect to x of x. We're going to take the derivative with respect to x of sine y. So the derivative of x is 1. The derivative of sine y is going to be, now this is a chain rule because y is a function. So when I take the derivative here, I'm going to get cosine of y times dy dx. Maybe then I get dy dx by itself. I get 1 over cosine of y equals dy dx. Ooh, that's just secant of y equals dy dx. And there's my derivative. Okay, so that's a little bit with implicit. We'll get into some tougher implicit next class, but that's all she wrote. So there you go. Have a great day.